Okay, hello everyone. Okay, hello everyone, and welcome to today's afternoon session for the conference. It is my pleasure to introduce the next speaker, Dr. Gerardo Rubino, who is a senior researcher based at INRIA. So before we get into the presentation, I just want to give a brief academic overview of what Gerardo has done. So he completed his PhD at the Université Rennes a number of years ago, and directly afterwards, he joined INRIA as a researcher, where now he acts as a senior researcher. His research interests are broadly related to the ideas of applied probability and Markov chain theory applied to a number of very interesting applications. These include rare event estimation, where he has a very famous and well-known book, but at the same time, the design and analysis of wireless communication networks. And today, what he's going to be discussing is stochastic flow networks and related ideas. So please take it away.
Thank you. Do you hear me? The micro is up, it's on, this one, yeah? Okay. Good afternoon. I will make a talk about a different kind of mathematics. Stochastic flow networks is, flow networks is an important topic in operations research, and it appears these days in the analysis of some communication networks, and also more generally network transporting something, some fluid. So the talk involves rare event analysis techniques using Monte Carlo, and the case of reduction the assumption of independence on the component of the systems analyzed. This doesn't work anymore. Okay, so not very visible. We will see. So more specifically, with my team, we work, among other things, on the analysis of dependability properties of specific complex systems. And most of the time, not all the time, but most of the time we use Monte Carlo techniques for the same reasons everyone uses this kind of method. Dependability means focusing on the failures of the component of the systems, on the possible repairs of the systems. Here I will talk about transportation systems, transport networks, where you move some fluid, I said, information is under some assumptions, oil, something that can be split into several parts. If to continue the journey through the network, you need to go to links having less capacities, and then they can join somewhere because there is a link having a high capacity and things like that. So not all communication networks will work in that way. In many cases, they do. So for those systems, we work on techniques allowing to measure, to evaluate things that otherwise are too costly to evaluate. The capacities now, that's the novelty in the area, will be considered as random, and that is because of the presence of failures. So the links are the components, the links are the objects in the model that can fail. And failing here means going down from the nominal high capacity at the beginning to some partial capacity to transport the fluid, or possibly to zero, which means a complete failure of the transportation link. Is kind of a problem. The problem we have to deal with most of the time in this area, the problems are static, which means that there is no time variable in the analysis. You observe the system at some point in time, perhaps infinity, and you compute probabilities, expectations. And if you are interested in the system at a different point in time, you will do again the job for the data corresponding to that point in time. So there is no stochastic process behind. We will have here one because it's the way we solve the problems here, but it's the original problem, the original question is a static one, no time. I will formally define the objects in a few slides, but because of the fact that the capacity of the links are random, you can believe that the maximum amount of fluid you can send through the network from the origin to the destination, or a set of origins to a set of destinations, the maximum amount of flow of fluid was also of flow will change. There is a maximum first, and it will change if the links become all with a very low capacity. The max amount of information or oil you can send will be smaller than at the beginning. So the question takes the following form. We have a minimal amount of fluid that you want to send. That is the demand D somewhere there. Hard to see, I think. It's better here, perhaps. This demand D, and what you want to evaluate is the probability that the max flow you can send in the network, which is random, is less than D. That's the rare event, this event here. Okay, we call it zeta, this probability in the paper. And the goal is to evaluate this in the context where the event is very rare, which means that the capacities are high and the probability that they go down is small. But given the fact that it is a rare event, you need special techniques to be able to estimate it. The most known, used, and studied families of techniques are importance sampling and splitting, the one I will speak about today. Then there are other smaller families, but sometimes very powerful, like RVR mentioned there. So I will focus on splitting. Splitting is designed for stochastic processes. You will split paths of the process. So in this kind of technique, the first thing to do is to construct an artificial stochastic process, allowing you to answer the question that we received in the static context, but working with a continuous time object, so evolving in time. So we will see the transformation we do. We'll see that that transformation will not work, will not satisfy another condition we wanted to set here, which is that many times, I mean, several years ago already, we started to think about relaxing the independence typical assumption, independence on about the components of the system. Because cases started to arrive where clearly it was a bad assumption. The problem is, of course, what we do when our customer says, or our boss, the system is clearly composed of things that are dependent on each other. I don't know how. So one of the goals we had here was also, we had in mind a way of taking into account dependencies, and that also was a criteria to find the right transformation. I will show you the immediate one and why it doesn't work, and then a change on the splitting idea to make it work in the dependent case. and using Marshall-Olkin copulas, for those which are familiar with that. So for part in the talk, a few words about splitting, then the model, then the transformation processes, which are these creation and destruction processes, and the splitting technique. So splitting. Imagine you have a stochastic process, Markov chain, X, that lives somewhere S, space, no, S. You have two subsets of states, like in the picture, disjoint sets SA, SB. You start somewhere outside in this point, and you want to evaluate the probability of reaching B before hitting B before hitting A. And that's my target zeta. The idea of splitting, of course, you have a trajectory here, a path where the event happens, and a path going to SA before reaching SB. So in this path, the event didn't happen. The idea of splitting is to build another subset of state S star that contains SB disjoint with the other SA set. And to proceed as follows: if your path goes directly to SA, fine, the event didn't happen. But if it hits S star, the yellow area, then we made in the picture two copies of the beginning of the path, and we continue independently the path, but randomly following the distribution of that dynamic system from this crossing point, the blue point here. And each of those two copies, two clones, will be observed in the same way. The one on the top will hit SB before hitting SA, and the other one goes directly to SA. So that's the simple idea of splitting trajectories when you start to get close to the target, to push the thing you will observe, to help them to reach the target. Once you think of that using one set, you can imagine a sequence of subset of states. The red one is all the area. The yellow is on top of it, and then the green on top of the yellow, and the gray one is SB, the target. Here we have three, and we follow the same idea on each of the paths, on each of the trajectories. Here you have a piece of trajectory reaching, hitting the third S3 set, coming from an intersection, a crossing point between the first and the second one, and then it is split, is cloned in two copies. For the rest of the trajectory, one hits the target, the other one comes back to SA. Splitting is one of the names. Restart is another name appearing in this area. There are many variations around the same idea. If I have time, I will say a few words. Things where this kind of things happens in some research areas are performance evaluation when you have queuing models, and the rare event is typically saturate a queue. So imagine a network of queues, just a queue, and you want to evaluate the probability of saturating, filling completely the buffer. And in some cases, that's a rare event. Or in dependability, I put a different example here because it happens many times. Imagine you have, speaking about this part, you have system where the states are good and bad. Good means the system works, bad, the system is down. You want to, SB is the set of bad states. TA is now the time to go back to the original state. So I call it tau 0 now. And the time, so tau, I didn't define that. Tau, yes, tau sub b is the hidden time of set SB. So tau b in this language is the lifetime of the system, how much it will live until it fails, until it's dead. And the expectation of tau b is called the mean time to failure of the system, the MTTF of the system. So expectation of random variable tau b. And if the system is highly reliable, this number is huge. If you simulate that naively using crude Monte Carlo, you will wait forever to observe a failure. But you want to know, the goal is to know if the MTTF is more than 10 to the 8 or more than 10 to the 7. So you must design something different. There is a result. You can prove these kind of things. For instance, here for the MTTF, saying that there is a missing expectation. The MTTF is the expectation of this numerator divided by the probability. There's two errors here. Probability that the event happens. The numerator, the expectation of the mean, is easy to simulate because of this T0 there, which is short. In general, the paths go back to 0 very, very quickly. The system highly reliable means that the repairs are fast and the failures slow. So usually you leave 0 and you come back immediately. So the numerator, there is no problem to simulate that using Monte Carlo. For the denominator, you have a rare, typical rare event situation. So make my copy paste. Didn't work here. About splitting in general, all the works, when you deal with that, you need to code the distance. You will always work by coding the distance of the state of the system, the state of stochastic process X, to the bad region, to the target region. And that is done, you call that building an importance function. Call it, name it H here. So you have some H of the process, which is a real number, and it measures how far you are from some threshold, which corresponds to entering the subset SB. So here you have some trajectories. You have to simplify, assume that you start, the subset SA has only one element. Then you, here you have a picture of, I don't know, 6, 7 trajectories. The only one reaching the target before going back to a subset SA is the red one. I will use that code all over the slides. So you have a 6 where the event didn't happen. You came back at the initial state, and all the subset SA the same. Here is H of, which is plotted, and one where the event happened. So in general, in the area, your importance functions will always behave that way, and the information you receive observing the point where you are is in this axis here. If you are close to the top, you are close to the target, and if you are at the beginning, you are as far as possible from the target. I already said that for a queuing system, for instance, your H probably will be the number of people in a queue or in a subset of queues the total number of customers in some region of the queuing network. Independability could be the number of failed components in the system. At the beginning, it is 0, and you have some failures, but the system can handle those failures and continue to work. And at some point in time, in our case, our network will not be able to transport the unit of flow at least. And so you have reached the bad area because there are too many things failed or too many things in some state. See, if you want to estimate the probability of hitting the target before coming back or before touching the other subset, and that's your result. As I said before, you have 1/7 trajectories, and you will use that ratio as estimation. The splitting idea then leads to look at this. So this is again the evolution of the importance function with time. You divide your vertical axis, the axis of the importance values, in regions using some thresholds. In the picture, you have 2 intermediate thresholds, L1, L2, and you will split the path when you, for instance, at the beginning, you will split this kind of trajectory when you cross this level before coming back to y equal to 0. So, for instance, you start here 3 trajectories. The first two of them come back before touching that level. This one was more lucky for our interest. And then the level was crossed at this point in time, tau 1. What you do is you split the trajectory there again in 3 copies. 2 of them go back, which is the usual behavior. You are lucky, or you design it correctly, the splitting technique, and you put the levels perhaps close enough to make sure that at least one of them, probabilistically speaking, will cross, and then you will split them again and again and again. I'm calling here, but I think it's local, di, the event tau I is less than tau A. That is the event that you reached level I. So yeah, you have defined K thresholds implying that decay is included and decay -1 included and so on. Just go your first D1 here. D1 is this segment in this, or from L1 to infinity in this picture. D2 is from L2 to infinity and so on. It is immediate to see that this is true. This is the target, the probability of touching the last level, hitting the last subset, and you write it in terms of these conditionals. You write in terms of all the conditionals, and you will get this expression eliminating the history after this this one, the past after this second one, and so on. And you can prove, it can't be proved, but the persons are publishing the first version of this. The very first version of this idea is Los Alamos in the 40s, from physics, of course, as everything in Monte Carlo. So at the heart, you have that this is an unbiased estimator of the target, and the p hat h for each level h are the standard crude estimators of the conditional probabilities, probability of hitting the next threshold starting from the previous one. Okay, this is just counting 1 divided by 3 here. here again 1 divided by 3, here 1 divided by 3, so my estimator is 1 divided by 9 of my target. So in general, typical notation when you work with splitting, you count how many paths reach on one level, given that you had a number n, capital N, of initial copies from previous one. So this is what you are doing when you are estimating the p hat local estimators. Okay, we want to hit, that's what is said in this sentence. As with any Monte Carlo technique, here, if sometimes for starting from one level, say close to the top, there is no trajectory hitting the next one. So in that sample, your estimator is the global estimator. You will stop, of course, and its value is 0. But you want to avoid that situation. I will say it at least once more time, and perhaps at the end. I don't remember. One of the weak points of splitting is that the variance is not well understood. So, you know, we don't have theorems about the variance. First of all, it's a family of techniques, not just one. There are many what we call today hyperparameters, and we don't have a general expression to work with of the global variance. So it's hard to configure an algorithm estimating this way. So it's said here, the variance is hard to obtain. We don't have results powerful enough. Let's say there are some results about the configuration of the choice of the hyperparameters. The parameters are how many thresholds you are going to use, where you are going to put the thresholds uniformly distributed between the mean and the 0 in capital L, or perhaps with a different density, and how many copies you are going to use, how many initial trajectories, how you will split, and what would you do when a trajectory that started in level 10 comes back to 10 before going to 11. There is a variant, this restart variant. People don't use that too much, but the idea is to kill the trajectory there immediately at that point, because probably the trajectory will down to 0, which is that's what the trajectories will do. Or perhaps it will try, it will have a piece going up again, but finally it will go to 0, the normal behavior. If you do that, you build a small bias, and the discussion is how much it plays in the final accuracy of the technique. Yes, something we do, something which is available are fine analysis of simple cases. You make a modeling as accurately as possible, a splitting process. And then you can obtain closed forms for the variance, especially the second moment, and then to get optimal results about the way you configure the algorithm. And then what? And then you use that as a guideline for your real case, which is more complicated, and for which you have perhaps some other hyperparameter to control. But that allows that we do the same. That gives you an idea. For instance, you try to configure your system such that, on the average, one trajectory touches next level among the ones that arrived to the previous one. That seems to be a goal. Seems to be possibly one day a theorem. Like in performance evaluation, there are results more or less equivalent. The optimal seems to be 1. So we try to configure the system to observe that value, to obtain that value. And otherwise we use pilot runs before making the simulation. Some references for people that wants to read about splitting in general. I will not comment them. Flows now. So formally, you have, it's better in the screen, a graph, directed graph, modeling the transport system. The fluid comes out this node S, the source, and goes to the terminal T, or the destination T, traveling through the arcs, and the flow can split. You can send 10, the flow equal to speed. You must think speed. You send 10, I don't know, cube meters per second here, and then here you decompose in 10, those 10, then 7 there and 3 here. And this node receives 4 and 4 now, so it will send 8, 7 there and 1 here, and so on. Each arc has a capacity, a real number. And for us, remember, it will be a random variable now. It will call X because of that. So mathematically, we say that a flow is a function on the arcs of this kind of system, satisfying 2 things, basically. One is that the value of the function is less than or equal to the capacity of the link, of the arc. The value is defined on the arcs. And the second one is Kirchhoff, local equilibrium in the red nodes. What enters, the total flow entering a node, a red node, must be equal to the total flow leaving the node, of course. There is a small lemma when you have that. Necessarily, the sum of the flows in these 3 arcs, so which is coming out from the source, the productor of the information, for instance, is always necessarily equal to the sum of the flow in the arcs reaching the destination. And that's what we call the value of the flow. The value of the flow is the amount of flow appearing here or absorbed, consumed here, transported from origin to destination. And you have a flow that sends 100 from left to right. Probably there are thousands of other flows, other functions, transporting in a different way those 100. Perhaps not in this small example, but with a real size network, it will usually happen. And perhaps you can send 110 with a smarter way of distributing the flow in the network. And you will have this is a finite thing, I mean, a bounded thing. You will have a max flow value if the capacity are fixed. And so for each vector of capacities, you will have a maximum amount of flow that algorithms can find. A little bit expensive, so all the area is very expensive, computationally speaking, but it's easy to calculate. The most famous one is for Fulkerson, and then many, many others, and Monte which is an implementation of mainly for Fulkerson, a principle, rather than an algorithm. So this is easy to evaluate, even if it is a little bit costly. The maximum amount of flow given the capacities is a function of the model and the capacities, the graph and the capacities. And of course, it provides also a solution, a flow reaching that amount of that max coming out of the algorithm. So now the value of the flow is the max value of the flow is there is a MF missing here. The max value of the flow is a random variable, and I want to evaluate the distribution of that random variable. There are algorithms to compute this also analytically, I mean numerically, but we are in NP-hard territory. So it's extremely expensive. You can do it. You cannot do it if the graph is medium size already, not far from this, the size of this one on the screen. So the goals, once again, is the situation where zeta is small, to be able to work this static problem in a continuous time stochastic process area to apply splitting, and to be able to use to attack the computation of this kind of metric, the kind of dependability is a sort of unaliability metric when the behavior of the arcs, the links cannot be, the capacity of the links cannot be seen as independent. And of course, you have data. You have at least some data. So we will consider in this work, we use the simplest assumption. You have a discrete random variable for the capacity of any arc. The values of the capacities are M1, 2, 3 here, and 0 put apart because it plays a small different role in the analysis. You say if the capacity is 0, that the link is failed. The capacities between M2 and the last one is partially working, and X1 is equal to M1 when it is fully operational. M1 is the highest. There is no yes here. M1 is the highest capacity value, then M2 is a degradation of the original situation, M3 less than M2, and so on. And then you have 0. Completely, the link behaves as if it were absent from the network. I have to accelerate a little bit. So transformation, that's an idea of Lomonosov, who was in Moscow at the time. I think he works in Israel now. I mean, I'm not sure now. He doesn't. He's not seen in the conferences. The idea is as follows: at time 0, the links are all failed. Sorry, I will move to a dynamic process now. Things will evolve with time. Each component now we have a life, and the life consists on being down failed that I wrote at time 0, and at some point, random point in time, it is repaired, and it goes to in our model in Lomonosov work. It was just a state 0, 1. 0 is down, 1 is working. So my original static problem, in the binary case, you have 2 states per component, and the probabilities of being in one of the 2. Let me perhaps. So you have it off. Oh, this one right. I don't know if you can. Well, perhaps it's not very visible. There. Vas a tratar de prenderlo. Let's say for one component, what I have as data is probability of it is 0 is P0, and I will move to my territory, but with only one value, M, different from 0, and that's P1. So the idea of Lomonosov, which we extended to a multi-level case, is simply to say that your component is a stochastic process now, as alive, start, failed. Thank you. So the component starts, failed at time 0. And one day it is repaired, and this is tau. In my case, I'm instead of state, I say the capacity of the component, and this is m. And probabilities are P0 in the static initial problem of being in state 0 failed, 1 if it is working. So you define a random, an exponential random variable with some rate lambda, where lambda is lambda will be here minus log of P0. And you focus on time 1. Perhaps it's there, perhaps it's here. And you observe that the probability that this now is x of t, probability that x of t is 0, x of t is 0, if the repair time is the same thing as repair time is more than 1, because this is exponential minus lambda times 1, the time, that is minus log of P0, which is P0. And the same for 1. So by this trick, you have now things evolving with time, and you observe this stochastic process now at time t equals 0. The probability that it is working is the same as in the static situation. What we did is to extend that to the case where you have as many values as you want. So I will go fast now. This is just reading. Okay, this is the distribution of my auxiliary random variable, and I want, that's my implementation, I want that when that variable is in this interval, the capacity, it is written here, with the variable is in this interval, the capacity is the maximal one. When I move to the second, when the random variable tau is in this second interval, then the second value is the value where the capacity that was repaired that time starts and lives forever, and so on. So to do that, these are, you have the formulas equivalent to the binary case of Lomonosov. This thing is called creation process, because you create the components, you make them appear from nothing at the beginning. So you have this stochastic thing now. At time 1, the metric you are interested in will be exactly equal to the metric in the static problem you had at the beginning. That's the idea. So if I accelerate a little bit, because I'm too slow, this is splitting applied to the creation process now. This is my demand. This is my max value of the flow, sorry, here, and that will be my controlling function. You will see that it's a little bit tricky, and this is my demand. For instance, this trajectory is a trajectory where the rate event doesn't happen, because the rate event I'm interested in is what happens at t equal 1. At t equal 1 in this evolution, my flow transportation system work at the maximum possible capacity. And why is that? Because the repairs are fast. So I will very quickly up. And only in the third execution, here, the total amount of flow that the system can transport is less than the demand. And here I have the rare event.
Good. Quick question. So if one forgets from the splitting for a moment, right? Can we think that there's a Poisson process behind everything you do, possibly state dependent, where you want to compute
There is behind
an expected value of the indicator of some event? So you can characterize this in terms of some expectation of a Poisson process with this fake time, and you want to actually do some this splitting that you do, or you could do important sampling or whatever to try to bring back this to a computable efficiency.
Yes, but in the middle, if I understand correctly what you have in mind, there is a natural Poisson state dependent thing, because we are using exponentials. That is why we are using exponential, because you can manipulate them and make many things I will not going to speak about, at least during the talk, for implementing all this idea. The point is that the evolution of that thing has this max flow computation all the time. So it's the pair of the two things.
Sure, but there is some Poisson that is driving the evolution, and there is some kind of constraint, which is a balance in the network, right?
Yes, which is the network part of the system.
Exactly. So one can think of a stochastic evolution with a constraint, which is the flow, the Kirchhoff law in the.
But you remember that what happens in the future now depends on in this Poisson by pieces, somehow exponential by pieces thing. You are repairing part of this huge graph. You repair here, then here, and here, and there. And the next execution will have another order. You have the tau, you will sort them by, it will be the order statistics of the tau, which is this exponential Poisson-like thing. But the value of the flow will have an impact. The graph, the structure of the graph, what happened before, will have an impact in the future. So there is no.
Yeah, but the information is flowing in one direction only, right?
Yes. We use this kind of observation for the implementation, but I don't see any way of using it for calculate.
No, this was not a question about calculation. It was it was about intuition. Can we think of this in terms of this evolution?
Okay. I understood that you were thinking which equation I can write.
No, not yet. But first, I understand to classify. I will try to understand to classify it. Right. Thank you.
Okay. So this is a good trajectory for the guy that is trying to capture a rare event, of course, and those are bad ones. So the idea of splitting on this multi-level creation process is to put the thresholds as before, and then, for instance, in this picture, these two trajectories. Imagine the first threshold I put in the middle. They are bad trajectories for me because they will not touch. I know that whatever the future of this point in this blue one is, it will not touch this segment here at time t equal 1, the one I'm interested in, the only one I'm interested in. But this one, yes, randomness makes that this one starts close to the x-axis. So in splitting, you will split the trajectories like these two here. This one was split in two copies, but this copy goes up, which is the natural evolution. The other one went to the next threshold and so on. So that's splitting on the creation process. let me, in this slide, I will take a few more minutes to reach an interesting part. Just a few words about dependencies. The Marshall-Hawkins calculus translate easily into a model where you decide that your components now can fail one by one or by groups simultaneously, creating dependencies, but this kind of dependencies. They call that a shock. A shock is the failure of a subset of components, perhaps only one, but perhaps 2, 3, 4, and you have a list, which is not necessarily all possible subsets of arcs in our context. You have a list of possible subset of components that fail together. And all the data comes in failure rates. And here we are repairing. So instead of using the creation process, we use in the same way a destruction process. You start with everyone working and you kill the components randomly according to the same trick in the multi-level. And at some point in time, you will not be able to transport the demand D on the flow, and the network, the system doesn't work in that case. So you have everything the same. The interesting thing is look at the trajectories. Those are 3 possible trajectories, the analogous of my first picture. Now the trajectories go in general that way in the top. The interesting one reaching hitting the rare set of states is this blue, with this crossing up before t equal 1 of the demand level. So first idea, okay, I continue and apply splitting here. Doesn't work. For that, if you must look at the picture of splitting here with those thresholds. If you put the same thresholds here, here, and there, you will push the trajectories to the right. And I want to push them down. So we changed the paradigm. I am something missing here, or I was too fast to the end. But in any case, I'm very late in time here. What we do, we move the thresholds to the importance, like in my first pictures. The goal is to push the trajectories down. For that, we put the thresholds, it's hard to control this, here and there. And the trajectories start on top. So they will find L2 first, if we are lucky. Here we were not lucky with the usual situation, that this one touching here. So this one we will split, and so on. That's the splitting part. For the results, I wanted to show you, but I will not do that. I want to try to stall only 6 minutes now. We get very good speed ups in the examples we put in the paper. If necessary, I will show you a page of the paper, which is already there. This is my computer controlling. The paper was, the revision of the paper was accepted this week, being here in KAUST. On Monday, we received the email. So the reference, let me start by the end, and then the chair. I think in any case, I'm a little bit late, right? Here is the paper by Lomonosov, the first one, when he proposes this idea of creation process, but for a different situation that easily to extend, that was we did. That's a previous paper we wrote with the same co-authors of this, even of this talk, and on which we worked on the creation process. This paper, written with other colleagues, develop something that you could ask, which is how to go from my data, whatever it is, to the shocks, to the Marshall-Working copulas. And that the paper works on that, on a different example, but the same situation. Is on natural rare events, critical rare natural events, like tsunamis and things like that in Chile. And then we discuss a little bit the mathematical aspects of going to the copulas. And the most important thing, which data, the failure, the marginals, like in our works with copulas, the distribution of the capacity of each of the links, and the correlations between those capacities. Just that. You have the matrix of correlations and the marginals. And with that, there are some mathematical tricks. There is not always possible to, if you bound the problem with the shocks, you are not going to use all the subsets of 50 arcs. You have 50 arcs. You are not going to manipulate in an algorithm all the subset of 50 objects, of course, due to the 50. You bound your truncate, like in the first talk in the mini course. You must truncate, and you will truncate low. And there are some mathematical tricks when you do that. That's in that paper. The paper of the talk is the first one. And there are not many, that's in my comments, but I will say it quickly already. There are not much work on flow, stochastic flow problems. In particular, almost nothing with splitting. Splitting with attacking static problems, but by definition on a dynamic setting, there are some works. This is one done with other people. So there is no flows here. And there is another paper I will put in a corrected version of the slide, where they, people like, not me, that not one, they used another approach to do splitting on flows, and other different assumptions, and nothing concerning dependent elements. Okay, I am 2 p.m. I'm happy to answer questions if somebody has. It's appearing in there.
Any questions?
Maya.
Safety.
That's a good idea. It's a super idea, this cube. The cube is a top idea.
Does it work? Yeah, it does. So how do you choose the number of thresholds in this splitting?
It's hard. There are, I said it very quickly. What people do is you take a simple model of the situation with simplifying assumptions, such that you are able to evaluate everything of interest, in particular the variance of the estimator. And then you can derive optimal results in that context, very simplified context. That gives some ideas about the simple formulas for the number of thresholds you should try. But it is not a theorem. It is not valid here because this is too complicated. But what we do is we start with these kind of things, and we do pilot runs, you see, and it goes very well because very quickly those pilot runs show you that you must adjust the parameters, what you do, and then you run it. You really perform the estimation, and it works very well. of course, with some students, we attack the choice coming from the fine tuning of coming out from the pilot runs, moving the parameters again to see if we are more or less in a local maximum at least. And in general, it happens. So it works. No guarantee that it was the optimal configuration, of course, but it doesn't matter that much if it is good enough.
Yep.
Yeah, thank you, Gerardo. A couple of questions more quickly. One, is it possible in your intuition to combine important sampling with this approach?
I don't know if combining, because both are killers of rareness, and both are good when things are rare.
Yeah.
So
but they work in a different way.
They work in different ways. So potentially, I don't see for it.
Changing rates, for example, important
Yes,
sampling,
that
changing
would,
rates.
changing range is the first. We discussed a little bit with Nadir. Is something that should be tried. For me, as far as I know, there is no work important sampling based on this kind of problems. Combining both is more ambitious. The problem I have tried in other cases. The problem is with important sampling, you kill rareness, so you cannot do it that way.
You may need
You cannot do it
less
sequentially,
splitting, for example.
Yes.
Okay.
Will be the same. You must do it somehow at the same time.
Yes, of course. That's what I mean, at the same time. So, and then the other thing, have you done, or do you know anybody using sort of large deviation principles to tackle this?
No, not for these kind of things.
All right.
Yeah, good question.
Can I ask one more question?
Yes.
Do you know if the splitting method resembles the peaks over threshold, where you know that you have a distribution of your threshold and then you choose the rare events that comes after that threshold or not?
Sorry, say it again.
Does the splitting method that you presented backward or forward resemble the peaks over threshold to study rare events or no?
I don't get the.
Maybe if you put the microphone closer to your mouth. Yeah.
Do you know if the splitting method resembles peaks over threshold in studying? So you know the distribution of your threshold and then you study rare events that comes after or before that?
Which I don't get is the distribution. You control the thresholds are a control variable, the position of the thresholds.
Yes, yeah.
And it's your business, the designer of the algorithm must make the choice. And the choice is guided by this kind of principle coming from simple examples. In the book, there is a book that we edited with a colleague on rare events. There are many examples from that point of view. So because you speak about the distribution of you mean that, the position, not the probability distribution. It's not a random variable, a threshold. It's a constant in all the process. Your job is to find a good position, a good number of, and where you put them. For instance, you could put them perhaps at the beginning, or perhaps concentrated at the end. In general, everyone goes uniformly because it's too hard to optimize with respect to 20 variables more than the rest. But there is no theorem, neither on that. So the number of thresholds, you choose them as I told you from these simple results with simple formulas. And then you move that a little bit, you perturbate that a little bit, you're using pilot runs and some tests before fixing that, but there is no distribution associated with. It's a control variable.
Thank you.
Okay, let's thank Gerardo again for the nice talk. Okay.